Welcome to the deep dive. We take the densest sources and extract the core knowledge you need.
And today, our source is about as dense as it gets.
It really is. We're taking an ambitious dive into Chapter 7 of Gray's Anatomy, focusing on the skin and its appendages. Our mission here is pure anatomical translation,
Right.
understanding the body's largest organ without a single picture to guide us.
And that's a huge challenge because the scale we're talking about is just immense. I mean,
Yeah.
for an average adult, the skin makes up roughly 15% of your total body weight.
15%.
Yeah, that's about 13 kilograms or almost 30 pounds spread over 2 square meters. It's not just a passive wrapping. It's this highly active, constantly renewing organ.
When you put it like that, you realize its job must be so much more than just holding us together. What are its main functions?
Well, protection is number one, obviously. It's a barrier against, mechanical stress, chemicals, UV radiation, but it's also an immune powerhouse.
How so?
It's performing surveillance and even secreting its own antimicrobial peptides, like human cathelicidin LL37 to fight off bugs.
I always forget about its role as a kind of biochemical lab.
It's absolutely vital. It's the primary place you synthesize vitamin D, which is triggered by UVB exposure. And then there's thermoregulation controlling blood flow and sweating to manage your temperature.
So, anatomically, how do we start classifying this massive organ?
We basically break it down into two main types. You have hairless or glabrous skin, think palms of your hands, soles of your feet. This is often called thick skin.
And why is it called thick skin?
It's a bit of a misnomer. It's not that the dermis is thicker, but its outer protective layer, the epidermis, can be up to 10 times thicker than the second type, which is hair-bearing skin that covers, well, everywhere else.
Okay, let's unpack that architecture, starting with that outer armor you mentioned, the epidermis. It's in this constant cycle of birth and death, right?
Wow. A masterpiece of dynamic renewal, really. It's all driven by stem cells in the deepest layer, the stratum basal. They produce new cells, keratinocytes, which immediately begin a journey upwards.
And how long does that journey take?
About 30 to 45 days. And over that time, they completely transform from these living sort of columnar cells into non-viable, waterproof, keratin-filled scales.
Let's focus on that foundation for a second, the basal layer. How is it physically connected to the rest of the body?
It's a single sheet of cells attached really firmly to the underlying basal lamina with these adhesive structures called hemidesmosomes.
Okay.
And they're held to each other by desmosomes. The key proteins here are keratins 5 and 14. They give the layer its fundamental strength.
In the book, they describe this interface with the dermis as being sort of wavy, not flat.
Exactly. It's like
Wow.
interlocking fingers. You have these upward projections of the dermis called dermal papillae, and the epidermis pushes down with what we call right pegs.
And that's not just for show.
Not at all. It massively increases the surface area for adhesion and, more importantly, for nutrient exchange, since the epidermis itself has no blood vessels.
So, moving up from that basal layer, where do these keratinocytes really start their transformation into that hard outer barrier?
That happens most dramatically in the granular layer, the stratum granulosum. Here, the cells flatten out, and programmed cell death really kicks in. Their nuclei start to shrink and condense. The technical term is becoming pycnotic.
And what are they producing in this layer?
Two really critical things. First, keratohyalin granules, which contain a protein called profilagrin.
Perfilagrin.
Yes, and that gets processed into filigrin, which bundles all the keratin filaments together tightly. Second, you have lamellar granules, which release these fatty lipids into the space between the cells. That's what creates the waterproof seal.
Yeah, that filigrin molecule is a big deal clinically, isn't it? The source material connects it to some very common conditions.
A huge deal. We now know that defects in the gene for filigrin are a primary cause of ichthyosis vulgaris, that very common scaly skin condition, and they're a major risk factor for atopic eczema.
Why? What's the connection?
If you can't make functional filigrin, you can't form a dense, proper keratin bundle. The result is a leaky barrier. You lose moisture constantly, and allergens and irritants can get in much more easily, triggering that chronic inflammation we see in eczema.
That really connects the microscopic detail to the patient's experience. So the granular layer prepares the armor. What's the final product?
That's the stratum corneum, the cornified layer. It's just densely packed layers of these flattened dead cells called corneocytes, all cemented together by those lipids.
And in thick skin, there's one more layer.
Right, just in the palms and soles, there's the stratum lucidum, the clear layer, which is just more optically dense. The amazing part is that the rate of new cell production in the base is perfectly matched to the rate you shed these old cells from the surface.
A perfect equilibrium.
Exactly. What's fascinating here is that the epidermis isn't just a wall of dead cells, it's also hosting this specialized cellular defense force and sensory network.
Okay, let's start with the cells that give us our skin tone, the melanocytes.
These actually migrate into the epidermis during embryonic development. There are pigment factories making melanin inside these little packages called melanosomes.
And they don't keep the pigment for themselves, do they?
No, that's the key. The melanocyte is dendritic, meaning it has these long arms and it uses them to transfer the melanosomes to all the keratinocytes around it.
So one melanocyte is supplying a whole neighborhood of cells.
Precisely. It can feed pigment to up to 30 different keratinocytes, and once inside, those melanosomes form a protective little cap over the nucleus to shield the DNA from UV radiation.
And racial differences in skin color. It's not the number of these cells.
That's a common misconception. It's not the number of melanocytes, it's their activity, how much melanin they produce and how it's packaged.
Okay. And then we have the immune sentinels, the Langerhans cells.
These are your cellular police force. They're derived from bone marrow, and they act as antigen-presenting cells, constantly patrolling for foreign invaders.
Is there a way to identify them?
Under an electron microscope, yes. Their unique calling card is something called a Birbeck granule, which people say it looks like a tiny tennis racket.
In a tennis racket. Okay.
If it finds an antigen, it grabs it, leaves the epidermis, and travels to a lymph node to sound the alarm and start a bigger immune response.
And finally, we have touch sensors right there in the epidermis.
The Merkel cells. They're found in the basal layer, especially in sensitive areas like your fingertips. They're slowly adapting mechanoreceptors.
What does that mean, slowly adapting?
It means they keep firing as long as a pressure is applied. They pair up with a nerve ending to form a receptor that's really good at sensing things like shape, texture, and directional pressure.
So beneath this incredibly active epidermis lies the foundation, the dermis.
And it is a massive foundation. It's anywhere from 15 to 40 times thicker than the epidermis. It's a dense, irregular connective tissue that provides all the tensile strength and elasticity.
And it has two layers of its own.
We divide it into two regions, yeah. The superficial papillary layer, which interlocks with the epidermis, has finer type 3 collagen.
And the deeper reticular layer.
That's much thicker and contains these coarse, heavy-duty bundles of type I collagen arranged in a sort of basket weave pattern. That pattern is what lets your skin resist being pulled in multiple directions at once.
Underpinning all of this is the hypodermis.
Right, the subcutaneous tissue. Mostly loose connective tissue and fat. It's for thermal insulation, shock absorption, and energy storage. And it's tethered to the deeper structures by these connective tissue bands called retinacula cutis.
Here's where it gets really interesting for me. Moving from the layers to the complex machinery housed inside them. The hair, the glands, the nails. Let's start with the pilosebaceous unit.
Right, that's the classic grouping. It consists of the hair itself, the follicle it grows from, the sebaceous gland, and the tiny erector pili muscle.
And the hair itself isn't just a simple strand.
No, it has 3 concentric zones. The outer cuticle, which looks like overlapping roof tiles, the cortex, which is the main structural part, and sometimes the central medulla.
And it all grows in a cycle.
A 3-act play. Anagen is the long growth phase, catagen is a short regression phase, and telogen is the resting phase before it falls out and the cycle starts again.
What about the sebaceous glands, the oil producers?
These are everywhere except the palms and soles, but they're incredibly numerous on the face and scalp. We're talking 400 to 900 per square centimeter.
And their method of secretion is unusual, right? Holocrine.
Yes, holocrine secretion. It means the entire cell has to disintegrate, to sacrifice itself, to release its product, which is sebum.
Why does it need to do that?
Because sebum is a complex lipid mixture, the most efficient way to release a big package of oil is to basically turn the whole cell into the product and have it burst open into the hair follicle.
And this is where acne comes from.
Exactly. Sebum production is androgen dependent, so it spikes at puberty. You get too much sebum plus a blockage from excess skin cells, and you get a comedone, the basic lesion of acne.
Okay, what about the erector pili muscle, the thing responsible for goosebumps?
It's a tiny band of smooth muscle. You can't control it consciously. When you're cold or startled, sympathetic nerves make it contract, which pulls the hair vertical and also gives that little squeeze to the sebaceous gland, helping to expel sebum.
Now for thermoregulation, the sweat glands, the eccrine type.
Right, these are all about cooling. They're controlled by sympathetic cholinergic fibers and secrete a clear, hypertonic sweat. Their coiled structure is a little factory.
The factory with different workers.
Pretty much. You have clear cells for fluid and ion transport, dark cells that secrete some glycoproteins, and myopithelial cells that wrap around the coil and contract to squeeze the sweat out.
And finally, the nails. They seem so simple, but they're not.
Not at all. They're basically a highly compacted version of the skin's cornified layer. The nail plate is produced by the nail matrix, which is at the base. And it's interesting, the proximal half of the matrix produces about 80% of the plate's thickness.
And the source mentions a very specific vascular feature in the nail bed.
Yes, glomus bodies. These are little encapsulated shunts that connect an artery directly to a vein, bypassing the capillaries.
For what purpose?
Rapid temperature control. In your fingertips and toes, they can quickly shunt blood away from the surface to conserve heat or open up to dump heat fast. They're critical for peripheral thermoregulation.
So this raises a really important question. With all these layers and specialized parts, how does the skin survive major trauma? And how does it get its blood supply in the first place?
The blood supply is incredibly well organized. It comes from 3 different systems and feeds into 6 horizontal interconnected plexuses,
Yeah.
like 6 layers of highways under the skin.
Which one is most important for feeding the epidermis?
That would be the subpapillary plexus. It runs right at the junction of the 2 dermal layers. From there, tiny little capillary loops shoot straight up into the dermal papillae, getting as close as possible to the epidermis to deliver oxygen and nutrients.
Okay, let's talk about how the skin is wired.
Yeah.
What are the key encapsulated receptors we need to know?
Well, you have the Pacinian corpuscles deep in the dermis and hypodermis. They look like little onions under a microscope. They detect deep pressure and high-frequency vibration.
And then there are the Meissner's corpuscles.
Right. Meissner's corpuscles are much closer to the surface, up in the dermal papillae, especially in the fingertips. These are rapidly adapting.
What's the difference, rapidly versus slowly adapting?
Pacinian corpuscles are slow. They keep firing as long as the pressure is on. Meissner's are rapid. They fire when a stimulus starts, but then they shut up. This makes them perfect for detecting changes, like feeling texture or something slipping from your grasp.
So now, trauma,
There.
wound healing. The source describes 4 phases, but what's the fundamental difference in how the epidermis heals compared to the dermis?
Okay, the phases are hemostasis, inflammation, proliferation, and remodeling. But the critical difference is this. The epidermis can undergo true regeneration. It has the stem cells to rebuild itself almost perfectly.
But the dermis can't.
The dermis heals by forming scar tissue. It's a patch job. It's mostly type I collagen laid down in a hurry, and you don't get your hair follicles or glands back in that area. And that scar tissue only ever reaches about 70% of the original skin strength.
Knowing that scarring is inevitable in the dermis must really impact how surgeons approach it. This brings us to the relaxed skin tension lines.
Absolutely. The RSTLs are the lines of least tension in the skin, following the natural orientation of the collagen fibers. If you're doing an elective surgery, you always want to make your incision parallel to these lines.
To get a better cosmetic result.
Exactly. It minimizes the tension, pulling the wound apart, which leads to a finer, less noticeable scar.
Finally, let's clarify the difference between a skin graft and a flap. It's a crucial distinction.
A skin graft is tissue that is completely cut off from its blood supply and moved. For it to survive, it has to get nutrients from the wound bed first through a process called imbibition, and then new blood vessels have to grow into it.
So its survival is precarious.
Very. It needs a perfectly healthy bed. A flap, on the other hand, is tissue that's moved but brings its blood supply with it.
How is that possible?
It's based on the angiosome concept, the idea that specific arteries supply predictable territories of tissue. So a surgeon can move a whole block of skin, fat, even muscle on its artery and vein, knowing it has a guaranteed blood supply. It's a game changer for reconstruction.
So when we step back, what does this all mean? The skin isn't just a covering. It's this incredibly complex, self-regulating, communicating system.
The key takeaway is really how function follows form. The keratinocytes journey creates the barrier. The specialized cells like melanocytes and Langerhans cells provide active protection. And all the deep structures from the glomus bodies to the collagen give it strength and adaptability.
And as a final provocative thought for you to consider, based on the material, we know that wounds in an early fetus can heal perfectly without a scar, a regenerative ability we lose.
Right.
And since adult scarring is so strongly linked to the inflammatory factors TGF-beta1 and 2, while fetal wounds have high levels of the protective TGF-beta3, what specific molecular strategy, one that could modulate that precise ratio, might finally unlock scarless healing for all of us?